I always debate what order to go with these things. I usually let it flow. The class before us got out early, so I took more time and wrote more on the board. Thinking, well, maybe that'll be more useful. I just went through my notes when we taught this stuff and said, well, yeah, we did that, and we did that, and we did that. So you have this all, and it's all in the chapters, but it'll give us an outline. So my intent is, we'll remember what we did. I'll show a couple things to help review and solidify the very last stuff we've done because it's fresher in our minds. Haven't had as much time to talk about it. And then I had some clicker questions for the heat chapters. We didn't do as many of those. So that could be a good way to review. And or I got the past homeworks here and circled the problems that more people got wrong initially to address those. So that's where we are. And of course, anytime you got something, you trump me. If you got a specific question, just raise your hand and we'll do it. So, down memory lane. Remember way back in chapter 13 when we were on liquids? Hopefully this doesn't sound near as foreign anymore, and all of you taking pictures, that's fine. Or hopefully we can get this posted and you'll have screenshots of it. Okay. Pressure. We introduced pressure. That's a force over area. Up till this point we were dealing with forces. And you guys are all over that, right? But instead of having to deal with them, all the microscopic forces in between the individual particles, we're going to use this thing called pressure. And so there's a force acting over a certain area of a substance made up of particles. That's the pressure. We had the bed of nails, high heels, snowshoes, the hovercraft. I could lift somebody up with a leaf blower as long as I spread that pressure over a big enough area, then you can get a big force. You don't want to lay on one nail because that's a lot of force over a small area and it's enough pressure to puncture your skin. But if you lay on like 600 nails that we had, it was safer. It's measured in Pascals, which is a Newton over a meter. When I forget, force is in newtons. Areas in, that was good. Areas not in meters. Meters squared, so all of you that took pictures, I'm sorry. Density. Again, instead of dealing with just the mass of one thing, let's see how it's distributed throughout with a volume. Mass over volume. I just love density. Mass over volume. All right. Given those put together yielded this. We learned quickly that pressure was depth dependent. The farther down you go, the more stuff's on top of you, there's more weight acting over the same area. So the pressure increases. More weight over same area, pressure increases. So plugging in, there's mass involved there with force. Gravity. You get this, density, gravity, the height, how much stuff's on top of you or how deep you've gone in that fluid. In the atmosphere, we like to think of how much is above us, because it's that matter that matters. No, I didn't plan that one. And if you're in water, it's how far down you go. You got the water in addition to the air acting on you, increasing the pressure. Also, while I'm on that, remember when sinking and floating. If you got an object like this, it's in the atmosphere. There's a little more air acting on the bottom of this box because it's deeper in the atmosphere than the top. So there's a little difference in pressure from the top to the bottom. And that difference yielded, I heard it, buoyancy, the buoyant force. It doesn't matter if I was here, there's less pressure on both surfaces, correct? But the difference is the same. And if I'm down here, the difference is still the same even though both pressures have increased because we're deeper. So that difference is the buoyant force, one way to think of that. Another way to think of buoyant force was just the difference it's going to weigh in air versus in the fluid. This is generic, or more specific, because most of you I think of jumping in a swimming pool and you feel lighter because you're floating. That buoyant force we usually relate to water. So if you just weighed yourself in air and then weighed yourself in water, the scale would read less. That difference is because the buoyant force is helping hold you up, countering your weight. So it's just that difference. Archimedes' principle. Oh, I didn't write that down, but this is it. This is Archimedes' principle. It's the weight of the displaced fluid, weights of force, is the buoyant force. That's a third way to look at buoyant force. The weight of the displaced fluid. So this takes up a certain amount of space. It's displaced that much air because it can't fit there now. The air's been displaced. If we could weigh that air, that would be that buoyant force, that difference. This gives, this is how you find it. Remember these subscripts. Some people get confused and they want to do the density of the object. No, it's based on the density of the fluid you're in. And it's not always the volume of the object. If the object isn't completely submerged, it doesn't displace its entire volume of the fluid, just what's submerged. So this is the volume of the displaced fluid. If you put it completely underwater, it will displace its entire volume. And that's a way to figure out its volume. But if it's floating on the top, like right here, only this volume underneath is displaced. You weigh that, you got the buoyant force. How are you doing so far? Ringing a bell? Yeah.
I missed part of it with the little part. So what over what is what?
Mass over volume's density. This is how I remember it. Well, actually, I've done it so many years, I remember it anyway. But this is how my daughter learned to remember it. I just love density. Draw a heart and then divide it. It looks like mass over volume. Well, then we did a lot with, let's see if this thing sinks or floats. And there's two ways to look at that. Not to confuse you, it's these multiple ways. I don't do this to confuse you. Sometimes some of you relate with one method more than the other. Density is a straightforward one. If the density of the object is greater than the density of the fluid it's in, like us in air, we're more dense than air, so we sink. That's why we don't float away. Like a helium balloon is less dense than air, so it floats. And if they're the same density, like a fish or a submarine or a completely full bag of water, all of those in water, they can be neutrally buoyant. They neither rise up or, I probably wrote float before, I guess to specify. It'll rise up. We have a term, and what I'm getting at is a lot of people say, oh, it's floating. And they usually refer to at the top. Well, it had to rise up to get there. Once it gets to the top, what happens? Does it go up further? Does it sink back down? I'm thinking of, take a balloon and put it underwater and then let go of it. It goes up, right? Because the balloon is less dense than the water, so it rises up. Once it gets to the surface, what happens? It stops. So what do we know then? It's neither rising or sinking. We have this case. How could it change? What's different when it's on the surface versus under the water coming up? That's exactly it. How much of it's under the water? When it gets to the surface, it's not completely submerged. So the volume of the water displaced is less. Thus the buoyant force is less. So it stops rising up. How much does it displace? Well, however much it needs to counter its weight. Because when the weight's equal to the buoyant force, it's neutrally buoyant. Yeah?
I don't know if this has been asked before, but how exactly do ships float? They've got to be more dense than water.
I'm glad you asked. How do ships float? That's just a confusion between the material the ship's made up of and the ship. If you're thinking of the ship, you got to consider everything contained with that ship. So example, if you take a piece of lead, it's really dense. It's more dense than most water, so it would sink. But you could hammer it out really thin and spread it into a big bowl or a ship, right? We haven't changed the lead. It's still lead. It's still more dense than water. But the ship is now displacing more fluid, isn't it? Because we've expanded the volume of the ship. And so the ship's density is less than the fluid. So it rises up until it displaces a little less, because it's out of the water. And at some point, the density of the ship will be the same as the density of the fluid. And it stays there on the top. But it's the space it takes up. So yeah, don't get confused between the density of the material and the density of the object you're thinking about. Another examples are party balloons in your birthday. The mylar they're made out of is more dense than air. So mylar would sink. But you put helium inside of it, helium's less dense, it would float. How about the two together? You have to consider the balloon now, not just the mylar or just the helium. It's the density of the object. And if the density of the object becomes less than the density of air, it'll rise up. And it won't do that until you've displaced enough fluid to increase the buoyant force. So you can look at densities, and as we've already alluded to, our force body diagrams. If the buoyant force is less than the weight, it goes down. If it's more than the weight, it goes up. So remember we did, because I know some things were confusing. Let's say this was made out of styrofoam, and this was made out of lead. Solid. Solid styrofoam, solid lead. Which one's more dense? Yeah. More mass will be in the same space. Let's submerge both of them underwater. Who has the larger buoyant force? Good, they're the same, because they're displacing the same volume of fluid. All right, let's let go of both of them. What happens? Yeah, it's displacing enough on the styrofoam to have this condition. And the lead, of course, is this condition. So this will go to the bottom, and this will rise up and be partially submerged. Now, who has the larger buoyant force? The same? Raise your hand if you think the same. Uh-oh, they're not agreeing with you or not playing. What else do you think then? You think the lead displaces more? Who agrees with that? More votes. You're correct. Because when this one's sunk, it's at the bottom. But it's completely submerged, so it's displacing its entire volume of water. Where the styrofoam's now floating on the top, and it's not completely submerged, so it's not displacing as much water. So the buoyant force is less on it than this one. But then how can this one be sunk? Because it's still not enough buoyant force to overcome its weight. This thing's really heavy if it's lead. Does that make sense? Well, let's see, was one more principle in there. Pascal's principle. It was just taking this pressure thing and we could use it with like hydraulic lifts. It's just the idea, if you had distributed the pressure equally through an enclosed fluid, you can lift something really heavy up, get a big force out, if you spread that pressure over a big area. It's kind of like the hovercraft. So you wouldn't have to push as hard over here over a small area. So Pascal's principle was the pressure is equally transmitted through an enclosed fluid. If you had a tube of water and you push on the water and compress it over here, it'll be transmitted through the whole thing. We can use that with the things we just talked about, like a simple machine, to multiply work. Force. Big no-no. Multiply force. You can't multiply work. That's energy. You can't create or destroy energy. Chapter 14 was on gases, and all that stuff applied to liquids as well as gases, as we've just been discussing. We were dealing with atmospheric pressure now. And these are some of the values in the book, and we discussed. It's about 100,000 pascals. We often refer to it as 1 atmosphere. Some of you know it as 14.7 pounds per square inch. If you ever take your blood pressure, it's measured in millimeters of mercury. Typical blood pressures are 120 over 80 or 70, but that's millimeters of mercury. If you had a column of mercury 760 millimeters high, the pressure at the bottom of that, just due to the mercury, is equal to the same as all the atmosphere above us. So you need all that air to have the same weight as 760 millimeters over the same area.
For the test, do we need to remember the
No.
atmosphere?
No, I don't believe I require you to memorize any of these values. I just thought I'd write it. It was helping me review the concept. And we did talk about most of those, not all. I don't think I emphasized these much, but the book did. Talked about them anyway. Likewise, about 30 inches of water is atmospheric pressure, equivalent. Boyles Law was based off of the ideal gas law. At a constant temperature, this work is if the temperature doesn't change, then if you increase the pressure on something on one side, like this, you start with this pressure in a certain volume. If you increase the pressure, well, it shrinks. That one should make sense. We did it in a bell jar with our balloon. If I decrease the pressure, the reverse happens. It expands. It's just the difference in pressures on the two sides, inside the balloon and outside the balloon. When there's differences in pressure, you can cause changes in movement. And in this case, when the temperature stays consistent, the volume will change. Yes?
The liquids and like the temperature changes. Like why does it cool when it's
Yeah, the temperature change too when this happens. There's a law for each of these. Keep the pressure constant, they call it a different law. Keep the volume constant, it's a different law. Keep the temperature constant, and they call it Boyles Law, and our book decided to talk about that one. But they can all three change at the same time too. Think of that one though, pressure, because that applies to our last chapter with heat transfer and expansion. If all these particles are moving around and they expand, they don't run into each other as often. Or as they're expanding and they hit each other, they don't make the other one they run into go as fast. So when things expand, they cool off. And vice versa. If you cool it off, they tend to, as you expand, it cools. If you heat it up, I want to say this correctly without confusing you, and I'm confusing myself. As things expand, it cools. If you were to compress it and shove them all in a smaller area, the temperature would increase. Because now they run into each other and push each other and transfer more momentum to each other. They're going to go faster. And that increases the temperature. So When air comes out and expands, they get farther away from each other and they slow down, it cools. If you shove them all back into the same spot, they're going to run into each other more and the temperature will increase. But there, the volume's allowed to change. It's not staying constant. Then we started moving fluids. This one was about the flow rate. If you're trying to shove a certain amount of water through a pipe, the same amount of water is going to get through regardless. But if you constrict part of it, it will speed up to get through there. So if the area starts out as something and then you constrict it, this is velocity, not volume. I love how there's these V's. Yeah, velocity. If you constrict it, it'll go faster. Bigger V. That product stays the same. We did that, if you remember, that I had this green fluid over here in the tube, and as it got narrower, the water or the air sped up. And we saw a corresponding drop in pressure. That was Bernoulli's principle. I wrote this. We didn't use it much, but this is the equation to guide our thinking. There's a kinetic energy term, the motion, fast or slow, and the pressure. So what we did, if it's sped up, there's more energy in this, less energy here. The pressure went down. If the pressure increased, it would go slower. And this one has the form for gravitational potential energy per volume, because of density. So if you change heights, that's back to pressure depth. If you got more on top of you, because you're deeper down, there'll be more pressure there. If you're lower, you got less potential energy, more energy will be in the pressure, and vice versa. So this helps me think of it. I didn't use it as much with you guys, but that might help some of you this time. It was just a annotation in your text. But the idea was Bernoulli's principle, where a fluid's moving faster, there's a corresponding drop in pressure. So you can blow across things and drop the pressure. And now there's a pressure difference, and you can provide lift for an airplane, or boomerangs, or whatever. Exciting stuff, isn't it? Questions? That was the first half.
Yeah, I have a question.
Good.
Now I'm confused.
Uh-oh.
I'm thinking in terms of what
We were good until I just said something and I confused you. Okay.
I'm just going back to the expansion and heat versus cooling.
Okay, expansion and
So why
compression.
is it, if when particles separate, objects cool, why is it that like when metal heats, it expands?
As I started to say myself and didn't want to say it because and you took it. So yeah, well, one here we're talking about fluid. If you got some air, I think it makes sense that if it spreads apart, it's going to cool. Does that make sense? Now let's look at a solid like you're thinking, like the table or a piece of metal on your chair. If you cool it down, those particles are more bound by its physical structure. They cool down, they're not moving as fast. They don't run into each other as much. Their temperature goes down. I mean, it was forced to go down. That means they're not moving as fast. And so they can constrict. Most materials will contract. And vice versa. If I heat it up, that's going to give them energy. And they start moving more and bumping into each other. And so they expand. If you heat up a gas, the same thing will happen. If the volume is free to adjust and you heat them up and they start moving around, it will expand. But you've put energy in. So I think that's the clarification for your confusion. If you put heat in or take it away, it'll do something. On its own, though, let's just say you have this stuff of air here. It's contained in a certain volume. Let's just open the volume up and let it expand. Or shoot it out of a nozzle, right? And let it expand. On its own, they won't run into each other as much and it'll cool. Does that help? It's a good question. Yeah.
For the last principle, you said the K increase and the P will decrease, right?
Yeah, where air is moving more quickly, there'll be a corresponding, so if that means this would go up. This would then go down. There'd be a corresponding drop in pressure in that airstream, and vice versa.
So PHYS will
And for that case, yes, I was keeping this the same, at the same height. But you could take a hose, and it's this big, and we can constrict it. It'll speed up, and it's just what I said. But the hose could also do this. The hose could come along and turn down. And now we're only changing the middle term. Well, it could go down and constrict, so that you can change both at the same time. And this will account for all of those changes. The bottom line with Bernoulli's principle, and the reason this works, this concept, is because energy still stays conserved. If you put more energy here, it's got to come from somewhere. That's why there's that give and take. Let's see, here's the homework from 13 and 14. Let's see, people didn't like, at least on their first guess. A suction cup sticks to a wall. Why? We had suction cups, so if I take a suction cup, press it to the wall, what holds it to the wall? Atmospheric pressure. It essentially pushes, I guess it wouldn't work with this because of the opening, but something flat. It would push some of the air out from in between. There'd now be less pressure there. Greater pressure out here, that difference is pressure spread over the area of the suction cup, and pressure times area exerts a force. And that's the force due to this atmospheric pressure being greater. That was one of them. Let's see, what else did you guys not like, at least when you were doing the homework? Oh, we discussed that one. The buoyant force on a rock is least when the rock is submerged near the surface, near the bottom, halfway to the bottom, or it doesn't matter. As long as it's underwater, it's displacing the same volume, and so the buoyant force would be the same wherever it's at under the water. Under the water. What else? Well, we did that. Density of a submarine. Now, how does a submarine go down and come back up, though? It can change its density. How would it do that? What's that? Yeah, it can take in more water or give out water and change its overall density and go up or down. Good. But most of the time, it's about the same density of water because it just stays there, right? And it just goes down maybe a little, maybe back up. Same with fish. They do it with air, in and out. An air bladder, swim bladder. Groovy. I did look right before class. A whole 5 of you have bothered to look at my answer keys and solutions to this homework. So, I know you're busy, but if the 13 and 14. Homework number 8. Now we'll go to chapter 15. Only 4 of you have looked at that. It's there for you to help you. So if this is confusing, you don't feel prepared, there's another resource you can take advantage of. They're always viewable and available as soon as they're due. So this homework you're currently working on for chapter 16 is due tonight. It'll be available as soon as, and that's why I do that, so you'll have tomorrow and some of Friday to look at that before the test. Well, let's just put it this way. If you do the homework and this stuff's still confusing and you don't understand all the homework completely, or it took you multiple tries on a lot of these, then maybe you don't understand it as well as at least the rest of the class, or as well as you would, I'd hope, like. Well, it's like me being there to explain what the answer is, to help teach you to review for the exam. It's another way to do it. Let's see on this next homework for chapter 10, which, yes, I haven't reviewed yet, but let's see. Homework 10, chapter... Why don't we do homework 9, chapter 15? That one's next. Let's go in order. You guys did better on that one than the last one. Actually, yeah, really well. There was one I wanted to emphasize, and I'm going over that right here. So, temperature, heat, and expansion. It was a lot of defining terms. Temperature is a measure of the average translational kinetic energy per molecule. I know it's a mouthful, but that tells us a lot that we've used for the next 2 chapters. So, what does it tell us? Average. That means the individual particles could be going faster and could be going slower. We saw that on the overhead when I was jiggling little BBs. You know, they go fast, they go slow, they change. But on average, they have a certain speed. If they have a certain speed, they have a certain kinetic energy. Do you remember how kinetic energy relates to speed? Is it direct? There you go. It's that squared term. Kinetic energy is 1/2 mv squared. So it's based on its mass. Remember, it's inertia, but also its velocity squared. So things that have the same kinetic energy do not necessarily have the same speed. Depends on how big they are, right? If 2 objects have the same kinetic energy, and one's big and one's small, who's going to be moving faster? That was one of your questions. The one with less mass, for that ratio, mass and velocity squared. So this tells us the average kinetic energy. It doesn't tell us directly the speed, but it does tell us the average kinetic energy. I often say that if something's hotter, it is moving faster. That's still true, but technically it means it has more kinetic energy. And it's translational, moving around like we're used to. If you include those other forms of energy, vibrational, rotational, funky things, then all of that is the internal energy. You can add energy to something and it can go into changing some of these and not raising its temperature. Remember, like when we have phase changes? When water goes from liquid to gas at 100 degrees Celsius, it's starting to boil. While it's boiling, you don't raise the temperature, but you're still putting energy in. It's going into internal energy, breaking bonds, causing them to do these funky things. Once it turns into gas, now it can raise its temperature again. We had this relationship. That's our guide to thinking for most of this. Q is the heat. It's energy in transit. It's moving this energy. You put something on a fire, you're adding energy in. And how much energy it takes depends on the mass, the material, the specific heat capacity. That's its resistance to wanting to change. It's like thermal inertia. Water has a lot of thermal inertia. So it takes a lot more heat to have the same rise in temperature as metal. And vice versa. Water will retain that thermal energy. It'll take longer for it to give it up because it wants to resist that change compared to metal if you had the same amounts of them. So there's 3 things that affect those. And also, you don't have heat being transferred unless you have a difference in temperature. Like over here, you didn't have motion unless there was a difference in pressure. Here, you don't have heat being transferred unless there's a difference in temperature. I got it here. We had this example. If you had a big bucket of warm water and a little cup of hot water, who has a higher temperature? The cup. So which way will heat flow? You weren't sure. Which one has more internal energy? Warm. So it has less temperature, less kinetic energy per molecule, but there's a lot of molecules. So overall, it has more energy in it than this one. So this has more internal energy, but this one's hotter. Which way will heat flow if you put them together? From warmer to cooler. Who agrees? That's right. If you mix those, naturally, it always goes from hot to cold. It can't go from cold to hot on its own. That would require work. Force it to go uphill, kind of. It's the temperature, is what I'm getting at, that drives the heat flow. It's always from the hotter object to a colder object. Not based on who has more energy. And sometimes that confuses folks. So just because there's more energy here and this is a lot bigger, it won't go that way. What's going to happen to this? This temperature will go down. Its temperature will go up because this will transfer heat energy to it. It'll absorb it, warm up. And they'll meet temperature-wise somewhere between them. If you have a lot more of this than this, as we do here, the temperature will end up closer to this guy's original temperature. Because this little amount won't have as big an effect. If these are exactly the same amount of mass of water, then you could end up right in the middle temperature-wise. But there's a lot more matter here. So this will have less effect on that than this will on this. Things expand. We had a bimetallic strip. We've already talked about expansion and why it does that. So based on the material, the C, the specific heat capacity, they'll absorb heat at different rates. And if one expands faster than the other, this can curve. This one expanded faster than that one. And water will do the same thing. Ice will do the same thing. Steam will do the same thing. But we had one funny thing with the transition between water and ice. So it's one exception we have. At 4 degrees Celsius, that's where water is the most dense. So it's because of, this is all water, this is all ice. This structure takes up more space. And so ice is less dense than water. But as it's transitioning, you have a slurry, a mixture. And the mixture is less dense than water by itself. If you start with water, you got all of this. And they get closer and closer together as it cools. And then it starts turning into ice, which makes it expand because now it has some of this structure in there. And the density goes up. Now it's all ice, and we can continue on. So 4 is the minimum point there. Yep.
Just regarding that diagram there, because if I imagine, let's say that volume up there when water is starting is 1 liter.
Okay.
It comes down and freezes, it doesn't quite go up. The volume, it's like the volume.
So if you started with 1 liter of water and cooled it down, its volume would shrink. It gets smaller and smaller and smaller. Now it's starting to turn to ice. Whatever volume it's at now, let's say it starts turning into ice. That volume is going to increase a little now again, until it gets to 0 degrees and it's all ice. But it won't be more volume than when it started with nice and hot up here, water. There is a point, roughly to scale at about 8 degrees Celsius is roughly the same density as 0 degrees Celsius. There is a little transition there near it. But it's the most dense at 4. So if you start at 4, it's going to expand either way, whether you heat it up or cool it down, which is different than most objects. What if you start at 0? If you heat it up, it's going to get it's going to contract and get more dense for a moment, which is not normal for most things either. Yeah?
Why would you, if you like fill up a water bottle completely and then freeze it, doesn't it like expand and explode the water bottle?
Have you ever done that?
Yeah, that's happened, yeah.
See? If you start with a full container of water, like, or pop can or whatever, yeah, and you freeze it, it's trying to expand. And if the bottle can't take that, it'll rupture and break the can or bottle, the container. And yeah, that happens a lot. So I usually leave a little air gap in there. Although sometimes if it freezes too fast, it'll expand this way more than slushing up to take up the extra space. But yeah.
I have a question back on the last thing you were talking about, when you said PHYS for the M, C, the change in temperature, and the M stood for mass and the C stood for the material constant, is that what it was?
You see the C? I didn't hear a response. C is the specific heat capacity. That's C. Is mass, like you said, yes. And back to the end here. All right, let's start moving this heat around, and there's three ways: conduction, convection, and radiation. I think you got those, right? Questions? Just the ways that you can move this thermal energy around. We discussed how things emit radiation and they absorb it, and they're doing that all the time because they have a temperature. So if you have an object and it's absorbing more than it emits, well, its temperature is going to go up because it's taking more in than it gives off. It's going to increase its internal energy. Some of that is going to go into the increasing the average translational kinetic energy. The temperature will go up. If it emits more than it takes in, it's going to cool off. And how do you determine when this happens? You look at the temperature difference between it and the surrounding material. If this is hotter than the air around it, well, there, we know which way heat flows, from the hot to the cold. So this will give up more than it's absorbing, and it'll cool down, and vice versa. When they're equal, the temperature doesn't change. It's at room temperature. Room temperature. Room temperature. They're the same. Because there's no difference in temperature, heat doesn't flow anymore. Well, no net heat. It's still absorbing, it's still emitting, because it has a temperature, but they're balanced. And so we're not changing the temperature. There's no net exchange. The larger that temperature difference, the more quickly the exchange happens. That was Newton's law of cooling. Really is all there is to it. So if this one were hotter than this one will cool down faster, at least initially, while there's a big temperature change. If you want to cool something down faster, put it in a colder spot in your refrigerator, because the temperature difference will be larger. And so the rate of cooling will be greater until it cools down to a certain point. But yeah.
So does that mean that cold water will boil faster than like warm water?
It's the energy, this is for cooling. So with heating water, you're putting energy into it. But if you just if you heat it up and then just set it and let it cool off, then this matters. So this is kind of like naturally just cooling.
Okay, so if you
I'm hot and I want to give off energy. I'm going to do that at a certain rate because everything radiates. The bigger the difference in temperature between me and my surroundings, the faster I'll cool. As I cool down, my temperature drops and there's less of a difference. And so my rate will slow down as I go along. All right, your glasses for this last part. Greenhouse effect. Things, because of their temperature, the wavelength of light, the frequency of light they give off is proportional to the temperature. So the sun is hotter than the earth, so it gives off higher frequency light than the earth does. Both give off light, but they're the same. So if the sun comes in and goes through glass, we heat up. We absorb the energy and heat up. And now we give off our own wavelength of light. But since we're colder than the sun, we give off longer waves, lower frequencies. Those can get trapped depending on the material. That was the idea behind the greenhouse effect. And here I want you guys to see it. So if I turn this light on, I'll dim the lights here. Look through your glasses at this light. You see all the different colors, right? Let me make it hotter. Just the color of the filament looks white, doesn't it? That's all the colors. Hopefully you can see the whole rainbow there. As I cool the filament down, watch the blue side. The blue gets less intense, doesn't it? Blue light has more energy, is higher frequency, shorter waves. So if this is cooling down, it doesn't give those off as much. The peak shifts based on its temperature. Now it's giving off more red and green. Make it hotter, gives off more blue. Just to help you remember that the temperature is proportional to the peak wavelength it gives off, and vice versa. We'll learn how these glasses work before the end of the semester, but not now. Anyway, that was that. You guys have been asking good questions, so I haven't gone to the clickers yet. Got that. Okay, 2 more things. Typical thermos. Now I want to end with that one. These 2 boxes, they have holes. They're hollow inside. What's the color of the holes? Black. Which hole looks blacker? Do they? I don't know. All right, for this one, I have different materials that are black. Which of the dots looks darkest?
The outside.
Oh, we differ. The center one? The outside.
From my point of view. The middle one. Yeah, it will change.
These might reflect light differently. Good, that's the point. The hole usually looks darker. These are like simulating perfect black body absorbers. Light can go in, but then it gets absorbed inside, and it's harder to just kind of reflect back out through the hole. Kind of like your eyeball with your pupil, the iris. Light goes in, gets absorbed. If nothing comes out, it looks black. That's why black's a better absorber, because it doesn't reflect the stuff back. But here's something interesting. These both look black. This one's the black one. This one's the white one. Didn't matter. They're at the same temperature. They're at room temperature, right? So they absorb the same wavelengths. And if they can't get back out, they still both look black.
Yeah, but these ones, the other 3 holes are covered.
Yeah, these they use dye to try to make the black. And they don't absorb all wavelengths quite as well as if you just made a hole and let it go in and get trapped. That's even darker because it's absorbing it even better. Now back to this, and we can end. It's just a quick review. Why do they make them this way? Well, the best thing that you can usually do to keep your liquid from either warming up or cooling down, put a lid on it. What does that stop? Which form of heat transfer? Convection. The air can't escape now and take heat away with it, or vice versa. So the lid basically stops convection. All right, it's insulated. This is two-walled with air in between. Or usually you'll put something around it to insulate it. Which one does that limit? Conduction, physical contact through the walls. Yeah. Why is it silver? That's for radiation or process of elimination. But look at that. It's emitting radiation. If it's a good reflector, that radiation goes back. So heat trying to get in can't. To warm it up, it keeps it cold. If it's already hot, it's silver and it reflects the heat back in so it can't get out and keeps it hot. So see, good physics just in a thermos cup there. If you got questions before Friday, just email me, ask me, come by, something. The glasses. If you'd be so kind, it might just be easier if you just come throw them down here. Where's the box, by the way? It's probably in the back somewhere. Thank you.